Hey everyone, welcome. This is section 7. That's right, 7.7. We're skipping around here a little bit. That way we can use L'Hopital's rule in indeterminate forms. So what you're saying probably is, Mr. Bartman, how do I evaluate this limit? Right here. I've got 0 divided by 0. What do I do? Well, you can't factor out to 0. You can't say factor to 0 unless really 1 over 1 and then be able to figure it out. This becomes a problem because you say divide by 0 is a problem, but then we also have a 0 on top. So we say, I don't know what to do. Well, it's a good thing this guy, L'Hopital, came around and gave us this rule. So let's talk about it. So we have several things called indeterminate forms, and they have to be fractions. So it's any fraction of the form 0 divided by 0, infinity divided by infinity, or any combination. So I could have like 0 divided by infinity, I could have infinity divided by 0. Any one of those possible outcomes is going to give us a problem. So if you have any limit that is in this form, you're not going to be able to solve it until now. Okay, so let's look at some of these indeterminate forms. So here's an example of an indeterminate form where it's 0 divided by 0. So we say the limit as x approaches -1. So I put -1 here, the top is 0, put -1, the denominator is 0. So what we're going to do, what we have done before, is you factor some stuff out, and then you divide by x plus 1, right? We saw the denominator, get rid of this denominator, and by factoring out, you end up with 2 times x minus 1. Then we can plug that -1 in, and then you're okay. Let's say we have a limit as infinity divided by infinity. So the limit as x approaches infinity of 3x squared minus 1 over 2x plus 1. And if I can divide by x squared, then I can kind of rewrite some things out, and then these cancel out, and I'm left with 3 over 2, and then I don't have to worry about it. So that's really, really easy. That's what we've done before. But now let's get into L'Hopital's rule. And L'Hopital's rule, actually, you know what? We're going to do something before that. We're actually going to go to the extended mean value theorem. You might say, Mr. Bartman, we haven't learned the mean value theorem yet. You're right, you haven't. But we're going to do the extended mean value theorem, that when we come back to it in section 3.2, you say, oh, I've seen that before. That Mr. Bartman, he's so smart. Alright, so the extended mean value theorem says if f and g are differentiable on the open interval a to b and continuous on the same interval such that g prime does not equal 0 for any x in a, b, then, I should put a comma there, then there exists a point c in a, b such that f prime c over g prime c equals f of b minus f of a all over g of b minus g of a. There we go. And if you want to know more about that, we're going to see the mean value theorem in section 3.2. So that's probably really when we're going to be able to use both of them. Alright, so we just know that if we find the derivative of f and g, there's going to be some point where that's going to be the mean, the average difference, right? So at some point, the slope at c, the instantaneous rate of change at c and at g, that rate of change, when you divide them, is going to be the same as the rate of change over the whole thing from A to B. Okay, so kind of think of this as much like just slope, right? Change in y over change in x, or we could say y2 minus y1 over x2 minus x1. Isn't that really what this is saying? Right, y2 minus y1, x2 minus x1. So you're saying find the rate of change of the whole thing has got to be the rate of change at a specific point. Okay, so now let's get back to L'Hopital's rule. That's right. He had a it seems like he's French because he has an L, an apostrophe, another capital H. He's got a lot of good stuff going on. So L'Hopital's rule says if f and g are differentiable on the interval a, b, containing c, which means c just is in between a and b, except possibly at c itself. So you can differentiate this whole thing except maybe at c. It doesn't matter if you can or not at c. And that's kind of the important part because we've had those divide by 0 and 0 over 0. So as long as they're differentiable, that is okay. But if we try and find a limit, then we've got a problem. Okay, so c is just somewhere in there, right? Run along in between a and b. Assuming that g prime does not equal 0 for all x in a, b, except possibly at c itself. Again, g prime could be 0 at c itself. If the limit of f of x over g of x as x approaches c produces the indeterminate form 0 over 0 or infinity over infinity or any combination of zeros and infinities, then what we're going to say is the limit as x approaches c of f of x over g of x, some division, is going to be the limit as x approaches c of f prime over g prime. Oh, and that can be so handy. All right, the only thing we have to say, provided that the limit on the right exists or is infinite. So as long as we come from the right side this way, it exists or goes to infinity or negative infinity, then you're going to be okay. And this works for every single indeterminate form. Infinity over infinity, negative infinity over infinity, 0 over 0, 0 over negative infinity. I'm not going to say the rest of them because it's kind of crazy. All right, so that is L'Hopital's rule. And what we're going to do is we're actually going to use that here in just a minute to do a couple of example problems. All right? All right, and now here is our first example. What we're going to do is evaluate the limit as x approaches 0 of e to the 2x minus 1 all over x. All right, so what I did was right here I just took the top part, and let's just evaluate. If I put in 0 for x, I get e to the 0th power, anything to the 0th power, no matter what it is, it's going to be 1. 1 minus 1 is going to be 0, and the limit as x approaches 0 of x is also going to be 0. So now we have the form 0 over 0. It's one of those indeterminate forms, and I can't factor anything out here. So luckily, L'Hopital is there to help us out. Okay, so what I really need to do is I need to find the limit as x approaches 0, and I'm going to find d dx of e to the 2x minus 1 divided by d dx of x. Alright, well the derivative of x, that's going to be easy. That's just 1. So we're going to say the limit as x approaches 0, that's going to be 1. And then the derivative of e to the 2x minus 1, I can kind of apply several things here. The derivative of that is going to be 2e to the 2x, and the minus 1 just kind of goes away. So there is my limit. Now can I evaluate this? Absolutely I can, because I don't have divide by 0 anymore. I don't have 0 divided by 0, no indeterminate form. So we should be okay. So plugging in 0 into the x, I get 2 times e to the 0 over 1, which is really just 2 times 1 over 1, which is really just 2. So there it is. It is just 2, and what I'll show you is on the calculator. Let's see. Here is the calculator. What I did was I just plugged it in. Remember to put parentheses around it. I don't need parentheses at the end because it is just divide by x. If we go over and look at the graph real quick here, it goes from -1 to +1. I'm going to 2. It looks like it's going right at 2. What I'm going to do now is let's just look at your table real quick. Let's have it start at 0, and let's have it go up by 0.1. That way when we go through this, we can just see what happens. We get an error here. If we just go and look at this, I say it's 1.99, 2.02. Looks like we're going to 2, and that is exactly what we had found algebraically using L'Hopital's rule. All right, so there you go. There's some examples. There is L'Hopital's rule. We're going to do some more examples in class. So good luck, and here is your question to do for the day. Your assignment is to evaluate the limit as x approaches infinity of the natural log of x. I'll zoom in so that way it's a little bit easier for you to see. Extreme close-up. So evaluate the limit as x approaches infinity of natural log of x over x. When you plug in infinity for top and bottom, you're going to get infinity over infinity, so L'Hopital might become your best friend. Good luck.